I think this is better. Yeah. Welcome everyone. First, I'll strongly encourage you to arrive at least 2 or 3 minutes before 12:15 or 8:15, so you have time to register. And also, please don't come late because kind of interacts with the filming. So if you, however, you come late, please sneak in very quietly. Preferably enter this way, not in front of the camera, please. So you all know that. Okay, so everyone has registered. I think I'll just turn this off for now. What's it say? All this technical stuff these days. That's there. Thanks. Yes, so, okay, so last time, any questions, by the way? Nothing? Just to mention this, I have my teaching assistant, which you haven't seen much of. He'll be able to talk to you through Zoom meetings. We decided that, so you can kind of film the whiteboard and explain things there. He's available at or you can send him a mail. It's, I put it on the homepage too. And preferably he'll be able to give you these Zoom meetings between it's on Wednesdays. So you can write him a mail and he'll send you a Zoom link and you can discuss things with him. Or maybe we don't have to put up a Zoom meeting, but it's easy. Yes, okay, so last time we were considering this scaling stuff. We'll also talk quite a bit about that today as well. Then we'll start doing something called, dimensional analysis, and then we'll start with scaling. It's very two related things, really. So we'll stick to these concepts today as well as we had last time. So last time we considered steady state, let's be specific, single phase flow in a pipe, and from assuming that's kind of where the physics comes in. We assume there is a relation between certain physical quantities. So we have the length of the pipe, we have the pressure drop, we have the flow velocity, we have the liquid viscosity, we have the pipe diameter. What else? We had this roughness. And finally, we have the liquid density. And we assume there is some kind of relation between this, meaning that if we pick 6 of them, the 7th one is determined. Well, since it's natural to have a fixed L, a fixed liquid, a fixed diameter, a fixed roughness, and a fixed density. So we have the liquid and the pipe. And then what we could do if you want to find this function is to, say, apply different pressure drops over the pipe and measure the velocity of the flow. So that would be a series of experiments. Doing this, we really have to, if we were naive, we would have to work with different lengths, different viscosities, different diameters, different roughness, different mass density. But since this relation has to be dimensionally correct, we realized that we had this following relation. Isn't it like this thing? Equals some 2 variable function. That's what we deduced. We used a tiny bit of physics saying that if the pipe is twice as long, the pressure drop will be twice as much, but that's of course self-evident because the conditions in the pipe is uniform. So doubling the length will just kind of double the same picture. So that's all really we assumed, and we arrived at this formula. This is the so-called Reynolds number. It's dimensionless, of course. So it has a physical significance. And also this was the so-called relative roll roughness. So how would we determine this 2-variable function? As I said, let's have a fixed fluid, a fixed pipe with a fixed wall roughness. And we could then apply different pressure drops and measure the rate. What would that kind of correspond to here? We want to determine this 2-variable function by doing these experiments, keeping this relative roughness constant. We can at least find how it behaves in the first variable, the Reynolds number. So what we will do then is to define this one. Let's say 5 bars across this 1 meter pipe, and then measure the rate. So then we will get this number, and we will get this number. So we can detect the different function values okay by doing this series of experiments. And then we can have a different relative wall roughness and do the same series again and again. And finally find this function k by measurements, because that's where all the complicated physics are. Saving us a lot of time, and then we can have the general expression valid for any pipe and any fluid. That's quite cool, really. So that's what dimensional analysis has for doing experiments. You need to do a lot fewer experiments after you've done some dimensional analysis of the system, usually. So it saves a lot of money, a lot of work. Not every person working in the lab knows this. So it's a bit non-intuitive. Also, we have this, these numbers, these so-called dimensionless groups, they're called. Dimensional dimension dimensionless numbers are often called dimensionless groups. That's actually usually what they're called in and for different physical mechanisms, there are kind of classical dimensionless groups, and they often have a name. They're often named after the first one who kind of derived them. So we have the Reynolds number. Relative roughness doesn't have any, say, Christian number, Christian name, but and these dimensionless groups, they have real physical meaning, because such numbers are independent of choice of fundamental units. So that means they have real physical meaning. Really. So that so for instance, this Reynolds number essentially define what type of flow there is. Type of flow is that there is. Let's give it a name, RE. So, for instance, we know that when RE is less than 2000, then the flow is so-called laminar usually. Of course, how the flow is also depends on this relative roughness, but assuming that has a small effect. I mean, you can think yourself, if this kind of rough wall, it's more easy to trigger turbulent flow. If you have a smooth wall, things flow more easily, and triggering turbulent flow is not that easy. You need higher rates probably. But essentially it's the Reynolds number defining how it is, and that gives you laminar flow. And we know that this RE is larger than 4000. Then you typically get turbulent flow. Actually, when we have laminar flow in the pipe, and this is starting to become a physics lecture. When we have laminar flow, it's quite easy actually to calculate how the flow is. We get this kind of we have the pipe here. Then we have no slip condition. Also, so we have zero velocity at the wall. Then we have maximum velocity in the center. And the shape of this is a parabolic surface. So that's quite easy to derive actually from Navier-Stokes equations, or even a simpler way of formulating it. So that's what these dimensionless groups mean for physicists. They define what type of physics is going on, often. Also, something about these dimensionless groups. They are usually ratios of two different types of two variables having the same dimension. For instance, the Reynolds number is a ratio to time scales, actually, because if you take the distance d, which is the diameter here, if we have a flow rate of u, then the time it takes moving distance d is through this viscous flow, let's call it TV, is d divided by u. So that's the pure flow. But then we have something called dispersion of velocity or momentum, because the kind of transversal dispersion of velocity due to the stickiness of the fluid, because if I move something in the middle, this movement will kind of travel transversally to each side, depending on how sticky the fluid is. And actually we have the time scale for this movement. It's much slower usually. Let's call it dispersion of velocity. It is d squared divided by mu rho, I think. It's actually from, we have, I mean, this is called is it the kinematic? Which is kind of a diffusion coefficient for velocity, how velocity diffuses due to this. And the time scale for a diffusion process is the length squared divided by the diffusion coefficient. That's a typical time it takes for a diffusion process to travel a distance d. And it's a long time. And this Reynolds number is the ratio of these two time scales. This is a large number. This is usually quite a small number, explaining why the Reynolds number is such large. So that's, yeah, time scales. Also, many places we have a ratio. If you have a system where two forces act on the system, then the ratio of these two forces define kind of what physical regime you are. Like I used to be a reservoir engineer. You have typically three forces acting there. You have viscous forces due to pressure drop, you have gravity, and also you have so-called capillary forces. So then you have two numbers defining the ratios of these forces to each other, which kind of defines what physical regime you are in. So it's a typical way of defining how the physics are. I think I'll put this one up again. Did I turn it on? Dimensional analysis is also used for some different type of procedure. Often you want to measure a system, how well things function, but it's very impractical to work on the real stuff. For instance, the picture that will show up now, soon. One of the reasons I don't want it because it looks very bad on the film, because it kind of glitters. So let's say we want to work with ship design. We want to build large tankers that are optimal in shape, such that we save fuel, of course. So what can this small label tell us about large ships? Not very much, it looks like. Because that's one of the exercises, actually, to see that that's quite impossible. The problem is that you need a fluid that has unrealistic properties in order to get an experiment that is equivalent to experimenting on the real thing. Because if you have this, if you have, assume, pi, assume we have a relation R1 equals a function of R2 up to Rn. These are then the input parameters, and we want to measure R1. We know from dimensional analysis, this kind of translates into P2. So we have m minus k core variables. Other k is the number of core variables. So we have reduced the number of variables all over. So assume we have, we want to measure this R1. And we have pi j of R2. Let's assume that R1 includes, pi 1 includes only R1, and R1 is not in any of this. Equals this for that. So we can have two sets of numbers, input numbers, that give rise to the same dimensionless numbers. That's possible, of course. Like for the Reynolds number, if I double D and double U, you have the same number, of course. So if I'm able to do this, then I can run the experiment with R2, Rn. So that corresponds to our toy model. And measure pi 1 in the toy model, and that's the same one as I would get for the real model. So, but these relations are impossible to achieve with a large tanker in water. I think we need a liquid that is ridiculously light, and also we have to consider so-called the surface tension is also important. That's kind of the tension of the surface. It's actually the energy needed per square area to make a surface between two faces, air and water. So it's impossible to design, and that's one of the exercises you have. So these dimensionless groups are used for several things important in physics. Okay, so now we turn to some math instead. Everything you've said so far kind of illustrates quite easily what we're going to prove now, or prove and prove, at least to get an understanding of this Buckingham pi theorem. So that should fit on the alarm. Again. So this illustrates the content of Buckingham's pi theorem. To prove that, or more or less prove. So this is kind of formulating everything you've done so far in more general terms. And we'll actually use linear algebra to illustrate really what we're doing. Because it's really just simple linear algebra, or at least basic linear algebra. So assume we have a relation, we have a dimensionally valid relation like this, and a set of fundamental units let's call them F for fundamental, up to, it says N of them. Fundamental units means that it's impossible to combine N minus 1 units to get one of the units there. So it's impossible to combine, to express one of these F's in terms of the other F's. That's what it means to be fundamental. Yes, such that there must be enough of them, such that the unit of Rj can be expressed. Let's this index stuff often messes things up a little, so I'm sure that I use the same notation. Let's call it AJ1, F2, AJ2, Fn, Ajn. For j equals 1 to n. So now I'm just doing the same as we've been doing all the time. Just for general number of variables and fundamental units. Okay. So this then defines the dimension matrix. call it A. And last time I did it such that I put the variables vertically. I think they do it otherwise in the book, but here the idea is the same, given by. So let's write the variables downward here. And the fundamental units there. And then look at all these exponents here. We should imagine that linear algebra was something to do with this, but it has. So it's an A is a matrix. Okay. So do you remember much about linear algebra or not? A tiny bit. We have the so-called column space and the row space of a matrix. The row space, let's talk about the row space here. If I had done it the other way around, it would be the column space, so it's all the same manner of talking. So let rank of this matrix, which is the dimension of the row space of A. Also the dimension of the column space, that's the same, that's the rank. So that's really how many linearly independent row vectors we're able to find. How many of the variables are dimensionally independent? That's the same. This translates to that we have K dimensionally independent variables. We'll look at a concrete example. This row space then might be three-dimensional. That's usually what we have. We have, say, mass, length, and time often. It's involved. So what we do when we pick core variables, choosing K linearly independent row vectors corresponds to choosing core variables. The way I formulated things now is really that we could also have units here, like say, if you only were interested in time, mass, length, but included temperature, whatever, this argument would still work because we're talking about the rank. not the number of fundamental units. But if you use a minimum of fundamental units, then the rank will be the same as the number of fundamental units. That is the number of core variables. Okay, so now we know how this freedom of choice of core variables corresponds to choosing a basis for a vector space where we have more vectors than we have dimension in the space. So let this, or this basis, because we have maximum number of independent, linearly independent vectors, that's the basis for the span of the row space. Let this basis be, so we can pick the second one, the second to last, and the last, or whatever, as long as they are linearly independent. Let this basis be, let's call it A I1, A I2, up to A I K. Yeah. So the rest of the row vectors that are not included here are then, of course, a linear combination of these k vectors. And writing the remaining vectors that are correspond to non-core variables as linear combinations of this, that corresponds to making dimensionless numbers. So I think this is the clearest way of formulating stuff. So for the rest, let the rest of the row vectors be AJ1, AJ2, up to AJ minus K. So then we can write then AJR, say, is a linear combination of these K basis vectors, and let's call them CJR S A I S, like that. So finding these numbers C then gives us how we should make a dimensionless number. So this is for, of course, R equals 1 to n minus k. Then pi j equals R, J R. So this is a non-core variable. It corresponds to the row that is not in the basis for the row space of the dimension matrix. And we divide them by then these core variables to make a dimensionless number. Should be I, yeah, I1, it's a very general list, you know, lots of indexes. S, that's a 1. And R, J, 2. A, this is A. So A, J, R, 2, up to R, K, A, J, R, K. 13. For R equals 1, 2, and minus K. Even though the notation is a bit clumsy, you get the idea here, what we really are doing. But this nice thing, I think, about the freedom of choice of core variables corresponds to the freedom of picking basis vectors for a vector space. It's the same idea in it. So our relation becomes like that, because we can drop all these core variables because they can attain any numerical value. That's the idea. That's kind of the flow of things in general terms. So all of you should be able to do a dimensional analysis of any system. The only physics we do is the first assumption that there actually is a relation between this. Let's illustrate this with a swinging pendulum. So I don't forget stuff here. Well, I can show you the next picture too as well. Let's have a break instead. So we'll start next with this swinging pendulum, and soon we'll start with this scaling stuff I was talking about. Okay. That's this different type of flow machines.